Good afternoon and welcome to the Space Madness podcast. Particularly excited about this one. Today, our guest is, it's our first episode since NASA reopened in the 2025 shutdown. And our guest is Dominic Benford, Program Scientist at NASA headquarters. So it should be a very interesting perspective, particularly this week. So I know you've got a number of roles and responsibilities. So how would you describe, your role? How would you introduce yourself?
Well, good afternoon, Jeff. Thank you for having me on. I'm happy to be here and, frankly, very happy to be back at work in the astrophysics division at NASA's headquarters. I'm a program scientist, which means I'm responsible for programs. There are two major things that I handle. One is an upcoming great observatory called the Nancy Grace Roman Space Telescope, which is the successor strategic mission that NASA will be launching following the James Webb Space Telescope, which has been up and operating beautifully for several years now. And Roman will be launching in a little less than a year and will conduct major surveys of the universe to understand things like dark energy and exoplanets and all of the most pressing topics. Other major role that I have is I'm the chief technologist for astrophysics, where I'm responsible for developing the technologies needed for our further generations of future space telescopes. We have a lot of them in the works, in plans, especially the Habitable Worlds Observatory, which is going to be an observatory dedicated to providing the capability, among other things, to measure the characteristics of atmospheres around Earth-like planets, around other stars, and search for signs of life.
So I'm particularly excited about that. And you've just described 2 or 3 generations of telescopes, depending on how you measure that. And of course, I want to get into those details, but one of the things I like to do on this podcast is find out how people got to be where they are and tell the personal story of what led them to committing to space and science as a career, and the interesting, memorable events that kind of stand out. So I'd love it if you could kind of take it all the way back, tell us the story of how you decided someday you'd end up there at NASA headquarters.
Well, thank you for that question, because it is always fun to talk about one's path here. Mine will sound like it was very straight and defined, and that this was the obvious conclusion. I was going to end up here doing this job. I never planned for it to be this. I didn't have this in mind when I set out. I didn't know what I was going to do, like many people. And if I want to dial the clock all the way back to try to figure out how did I end up here and now, you'd have to go back to probably when I was in elementary school and that through high school. And I loved understanding how things worked. And I loved taking things apart. My parents, perhaps being a little foolish, allowed me to have access to things like screwdrivers. And I discovered that you could open all kinds of things with screwdrivers, not just like stock drawers, but also pretty much anything electrical or mechanical around the house. And as a result, I got to be pretty good at taking things apart to see their innards. It took a while before I got to be good at putting them back together again. So the long-suffering parents helped with that. But I was always very curious about understanding the how and the why for all these things that you think you have around in your standard everyday products. So it's things like clocks, and then when they were invented, VCRs and televisions, which you could shock yourself with. So I have to say, don't advise that everybody do this at home necessarily. And that kind of curiosity led me ultimately perhaps to majoring in physics when I went to university, because that's really the study of how things work at very basic levels. And since I had this interest in doing things with my hands, I ended up working for a research group that I joined around my 3rd year of college, my junior year. And not through any particular planning, they happened to have a project that was well set out for me to try to develop a very low temperature refrigeration technology as a prototype for a cooler that would fly on one of NASA's great observatories. There were 4 original great observatories that were planned way back in the early days of spaceflight that would cover much of the electromagnetic spectrum and provide a wealth of astronomical data for astronomers everywhere. The very first, and probably the very best known, of course, is the Hubble Space Telescope. But then there was also the X-ray Observatory, the Compton Gamma Ray Observatory, and the 4th one, the Spitzer Space Telescope. That was the one that I would work on. And that was in about 1990.
I did not know. Okay, so first of all, thank you. There's a lot there. I did not know that those 4 were part of a grander plan starting when, the 70s?
Yes, those ideas certainly were formed in the 70s. The way that NASA responds to desires from the astronomical community is via a format called the Decadal Survey. Every 10
Mhm.
years, approximately, the National Academy of Sciences, by direction from Congress, canvasses academics and researchers all across the country to discern what the pressing scientific questions are. And they do this in multiple disciplines, in
Mhm.
this particular case for astrophysics. And so each decade, there are one or more major missions that get prioritized for NASA, saying this is the next most important thing to work on. So, for instance, Hubble was one back in the 70s. I don't actually remember which year it was.
Mhm.
James Webb Space Telescope, of course, was one that came out of the 2000 Decadal Survey. The 2010 Decadal Survey advanced the mission that's now known as the Roman Space Telescope. The
Mhm.
2020 Decadal Survey told us to begin working on the Habitable Worlds Observatory. Maybe in 2030,
Mhm.
they'll give us yet another amazing
Sure.
mission to work on.
Well, what I like about the way you phrased the first four was it connects to something that I've always thought about, which is that before you've left your home planet, assuming you have a moon around that planet, the logical first place to go is the moon of your planet. In our case, the moon. Now, when I look back before I was born, of course, at Apollo in the 70s, I think, well, it must have been really easy to decide to go to the moon. But then what? Do you go to Mars? Do you go to Venus? It's nowhere near as obvious because the moon is just so much closer than everything else. Now, you've given me an extension to that model, which is as soon as you can put telescopes in space, your civilization can do this. Well, then, of course, you want to look across all of the spectral bands. And I didn't realize that it was kind of put forth that way in those early days. So I really appreciate that framing. Now, before we go any further, for our
Sure.
audio listeners especially, I really like your tie. I cannot describe the knot, but and I don't wear ties very much. And when I do, they're definitely the most boring knot possible, the only one I know. What is the name of that knot? Because I feel like it's goes pretty far back.
So this one is, I believe it's formally called the fishbone knot, but it's a
Okay.
variant on a set of different knots, the most common of which is called the
Mhm.
eldridge. And I don't know when it was invented. These have been
Uh-huh.
around for a few decades. One of the things that I do is tie different kinds of knots. I have a stable of about
Okay.
a dozen or so that I rotate
Oh,
through
nice.
occasionally. This is one of the
Okay.
more interesting and symmetrical ones. It
Yeah.
ends up with the same shape as the full Windsor, which might be one of the ones that
Okay.
you
Yeah, the
taught.
basic one, right? Yeah.
Well, there's also the half Windsor, the four in hand, the Pratt, and things like that.
Oh.
And most men learn to tie the knot that their father taught
Mhm.
them, and
Yeah.
that's the one you have. And you don't even bother to know the name or really anything about it. It's just that's what I
Sure.
always. And
Sure.
at some point, I realized that there were lots of other knots. It was
Mm.
actually inspired in part by the movie The Matrix. Actually, the second Matrix has this villain,
Okay.
the Merovingian,
Huh. Yeah.
and he's
Uh-huh.
French and infinitely sophisticated. And he wears,
Uh-huh.
if memory serves, a black suit with a
Uh-huh.
black shirt and a black tie. And the tie is tied in this interesting knot that is basically the full Windsor knot, but tied front to back reversed. So the tail
Huh.
end in front of the blade end, the skinny bit in front of the wide bit. It looks a
Interesting.
little bit like your tie has a tie on it. Very sophisticated, very chic.
Yeah.
It's called the Idioti knot, but now most people refer to it as the Merovingian knot.
Oh, okay.
So if you can tie the Windsor, you can tie that.
Interesting. I really like that. Again, not an uncommon set of knowledge clearly on these tie knots, but one of my favorite things about these episodes is learning stuff like that. So thank you. Very interesting. Yeah, my son,
Yeah.
I'm probably going to have to teach him to tie a tie soon, and I may have to remind myself because I haven't worn a tie, I don't know, in years. Anyway, wonderful
There are
tangent.
lots,
Thank you.
there are lots of great YouTube videos on these
Sure.
things. How do people invent knots? It's very easy. Over 100 named knots and vastly more
Interesting.
that are unnamed. During the pandemic, we were,
Uh-huh.
of course, forced to work from home like many people were for a very long period of time. And so when we left, I committed to people, since I already did the knot thing, I will tie a different knot every single day until we come back in person. I
Oh, that's
figured this could
fantastic.
be weeks. This might be
Yeah.
dozens of knots. It ended up being several years. I have tied and now have had to invent approximately 1,000 new knots. But
Really?
combinatorics says that there are far more possibilities, and I'm not
Sure.
going to have enough days in my life to go through all of them. Most
Sure.
of them are not very appealing, but occasionally I'll hit on one that looks decent, and
No
and
pun
I try to
intended.
record everyone.
Not very appealing. No pun intended. Well, I'm sure out there somewhere there's a YouTube channel with hundreds or thousands of knots. I like the idea of
Yes.
a coffee table book that's like this thick with a different knot on each page. And also, while you were talking about that, I was trying to think of a way to tie in the various geometry fields into a tie discussion, but you went right there with combinatorics. So
Yes.
fascinating.
You would think it would actually be knot theory.
Well, I was going to say that, but I assumed if it was that simple, you would have said it. But so interesting that it's not. Anyway, back to space telescopes. So clearly, your passion for understanding how things work and motivating and inspiring others is coming through really clearly here. So it sounds like you got really lucky in that one of your first academic/professional assignments was on one of these great observatories. So where'd you go from there? How did that play out?
So I would confess that it is really lucky. My life
Sure.
is a series of lucky maneuvers. And
Mm,
all I can say about that is the strategy, in a way, comes from a book that was published in the early 1980s called The Art of the
mm,
Long View. I
mm,
can't remember the name of the person who wrote it, but the the basic tenet, as I got it from that, is don't try to plan your next move. Don't try to plan each individual stage. Just have an idea of one thing that you think you could see yourself doing at some long time
mm,
in the future, 10, 20, 30 years.
mm,
And every time life offers you a choice, you think, is taking this off ramp more in the direction of where I want to go, or is staying where I am more where I want to go? And that's been my
sure.
guiding principle ever since.
Sure.
And when I left college, my guiding principle had said that I wanted to work more on that kind of research because I was at that time very interested in the cold material between the stars. The
Hmm.
interstellar medium is all the gas and dust that hasn't yet formed stars. And
Mm,
billions of years from now, it will be stars. And after our star is gone and it throws off so much of its atmosphere, it will replenish
mm,
the interstellar medium with all of the heavy elements leading up to iron that have been
mm,
fused in the sun over the 10-ish billion years of its life. But we just haven't had the tools to study that so well as we've had the tools to study stars. So I wanted to
sure.
help build those tools. I
Mm,
went to graduate school at Caltech and joined a group that was building that kind of technology and using it on a ground-based observatory. So I spent a lot of time at a telescope in Hawaii
mm,
trying to study the interstellar medium. It was pretty hard going. The technologies were not as high performing as you might want them to
sure.
be. We kept working on that.
Well, I imagine what you were trying to measure is the various glow particles and radiation from those interstellar regions. Is that right? I once knew more
Yes.
specifics, but it's not coming back to me at the moment.
Yes, the interstellar medium is mostly the regions we're looking at, the denser regions, is mostly very, very cold. And so it doesn't give off visible light because nothing's warm
Mm,
enough. Some of it can be seen with, say, things like the Hubble Space Telescope when you see reflections, so starlight that illuminates the surfaces, and you can see that. The James Webb Space Telescope does this a lot as well. Many of the most brilliant, colorful photos from those observatories
mm.
are actually the glow of the interstellar medium illuminated by other things, getting energy from other things. Now, we
So
were looking. Go ahead.
interesting. So, I suppose I should have assumed that. So you're saying that we can see in the non-visible wavelengths reflections off of this non-visible matter. Is that right? Is that what you're saying?
That's absolutely right.
Okay.
And that may sound strange, but when you think about it, almost everything you see in regular life, you're actually just looking at the light bouncing off something. If you look at the pictures
Sure.
behind me, they're not
Sure.
glowing. It's the room lights that illuminate them and you
Right.
see the
Yeah.
bouncing off light.
The
Now, if you look
screens are
right at the light
glowing.
bulbs, that's what you're seeing.
Yeah.
So the stars
Yeah.
glow and they illuminate all these other things.
But the specific extra level of measuring in non-visible wavelength, reflecting off of things that don't reflect any visible wavelengths is kind of the beauty of astronomy to me. It's looking at
Yes.
invisible things reflecting off of other invisible things.
Well, in this case, we often looked at clouds of dust. A lot of the
Mm,
mass is dust particles, so little grains of
mm,
carbons, irons, silicates. And you think of dust as being basically like smoke, essentially, and
mm,
it's
mm,
dark, but it's thin, so you can see through it most of the time. And so you don't tend to notice it in
mm,
most areas of the sky where you look with a telescope. You see through a lot of that dust, unless you look right in the plane of our galaxy, where you're looking through lots and lots and lots of this material. And in fact, this was discovered centuries ago by people who thought that they might just be places where there weren't stars. And eventually they realized, no, it's that there's something dark in the way.
mm,
That's where it's most concentrated. Now, it turns out that all of those clouds of dust are glowing. It's just that they are so cold that they glow with wavelengths of light that are far beyond the red end of the spectrum and so are
Sure.
invisible to us.
Sure.
And therefore, you have to build a camera that is sensitive to light, much,
Mm.
much longer wavelength and much redder than what we can see. And that technology has taken a long time to develop. There are various ways of doing this. And at the time, we were exploring ways of measuring it thermally by just measuring the heat of this. But you can also measure it more like as a radio wave and using more like radio technologies. And a lot of this technology has been pushed forward over the decades. And so now there are fairly mature technologies that provide what are referred to as millimeter wave imaging systems. And if you ever go to the airport and you have to do this and they do the scan of
Yeah.
you, that's a millimeter wave imager that is looking at the glow that you are giving off as a cold object, cold
Sure.
relative to
Sure.
temperature of the sun.
And looking for things that might be blocking that, like dense metal objects. I will
Yes.
probably go through one of those on Monday.
Yes. So that is an outgrowth of the technology development that groups like the one I was in developing back in the 90s. And it took a while for it to be mature enough to be commercialized and is now in every airport.
Sure. Now, one of the things on millimeter wave astronomy that I have always, well, that I didn't appreciate till perhaps later than I should, was the need to keep those things cold, absurdly cold, to the point where often for mission development, the system to keep the sensor cold is just as challenging as the sensor itself.
It is.
Not perhaps what one would assume from the outside looking at, a list of technologies, but I always found that very interesting. So I'm aware that was a major factor in the time it took the James Webb telescope to be developed, was it not? That the developing systems and methods to keep that thing cold enough.
Yes, the James Webb Space Telescope had to be very cold. The telescope, the mirror itself, had to be cooled down significantly, and the camera, especially the mid-infrared camera behind it, had to be cooled even more. If I can go into absolute temperature units, room temperature is up here at about 300 Kelvin. Water freezes at 273 Kelvin. Dry ice is down at about 195 Kelvin. And that's about as cold as most people have ever experienced. That you're not supposed to even touch dry ice because it is very, very. Liquid air is down at about 80 Kelvin. Good nitrogen, 77.
Okay.
Helium, the lightest common element, is down at 4 Kelvin. The mid-infrared instrument on Webb, I believe, is operating at about 6 Kelvin, so a little bit above that. The cooler that I started working on when I was an undergraduate, I referred to that for the Spitzer Space Telescope. Even though it didn't end up flying, it was descoped because it was very complicated. That was a refrigerator to go down to 0.1 Kelvin.
Wow.
And it did work, but it was challenging.
Has anything at that level flown?
So we have yes, we have had that fly in instrumentation that has been developed most recently for combined Japan and NASA missions with names of various kinds, but they were X-ray missions, and many of them had a lot of challenges in the technologies, but the refrigerators worked.
Okay. Well, if you'll go down a rabbit hole with me, I'm going to vastly oversimplify and butcher how these sensors work. My understanding is that there is a voltage output from these materials in response to certain wavelengths coming in. And if you don't keep them cold enough, then the incoming wavelength is lost in the noise. Is that a fifth grade level explanation, or am I way off?
That's a pretty reasonable explanation. I can give you a little bit more since you wanted to do the rabbit hole thing.
Yeah.
Many detectors, not all, but many detectors of light work in a way that is broadly similar to the way the camera in your cell phone works. The camera in your cell phone is referred to as a CMOS sensor. These were invented originally by NASA engineers at the Jet Propulsion Lab in Pasadena in, I think, the 1980s-ish. The fundamental technology is a little piece of silicon, which when light travels in and hits it, it generates a little bit of charge, which you can measure as a voltage, and you build into this silicon, since it's the material of computer chips, small amplifiers that allow you to sense that tiny voltage. And so in that way, you're reading out the amount of light by how much voltage you have. So the trick about this is that you want to make sure that you're reading out only the voltage that is generated by the light that's falling upon this. And the problem is that voltages can also be generated just by random thermal noise, the noise of heat, because everything is always in motion. And so you do tend to read out some amount of thermal noise in the form of what's called dark current. That's the electricity that you get when there's no light on it. And it is
you see that on spec documents for sensors from all the
yes,
manufacturers. I
absolutely.
always love that term.
It's a and it's one of the things that is fundamentally limiting, and it's so temperature dependent
Mm,
that that is what principally drives the temperature at which you have to cool your detector. And because the energy in the light, the energy in the photons of light, it would be lower and lower as you move redder and redder in color. As you
mm,
move to those longer red and then infrared wavelengths, the photons get less and less energetic. And so you need less and less energy in the sensor to thermal
mm.
energy to generate dark current. And so you have to cool them further and further. So it's a bit of an arms race that
But
the
then
longer
you
the
also
wavelength,
need
the colder the sensor.
now. Do you also need more amplification as you get colder, which would seem to be a
Yeah.
challenging tension
Uh,
in system in designing it?
so not necessarily, I would say.
Okay.
You might think that you need more amplification, but you can also you can change the size and the scale of the sensor to change the
Okay.
ratio of how much voltage you get. But also,
Okay.
as you tend to move to longer wavelengths, each individual photon has less energy.
Mm,
But if you're looking at a source
mm,
that has an arbitrary artificial source that had the same brightness at all wavelengths,
hmm.
you need more photons as you go to longer wavelengths to give you the same amount of energy because each
Okay.
individual photon has less energy.
Right.
And
Okay.
so when you ask how many photons do you get when you're looking at an object of a certain temperature when it's
Mm,
6,000 Kelvin, like the surface of the sun, versus
mm,
60 Kelvin, like a lot of interstellar space, you may find that there are vastly more photons coming from this cold thing if you're, all other things
mm.
being equal, because the photons have so much less energy.
So
So,
there's something. So I missed something there. So you're saying that but a cloud in interstellar space can have more photons than the surface of the sun. What
well,
are
so
we
I was saying
comparing
all things being
equivalent
equal.
surface areas? Oh, okay. Okay.
So they're not actually equal because the colors of light that are produced do change. That's what's referred to as the black
Hmm.
body spectrum. And as you
Hmm.
warm things up, you produce more and more photons at all wavelengths, but you also produce more and more photons at bluer and bluer, shorter and shorter wavelengths. So you actually do
Okay.
produce a lot more photons.
Okay.
I was trying to say all things being equal in a way that's not very physical.
Sure. Okay. So this being all of this being kind of the fundamental way all of these different telescopes work, right? Of looking further and further at different ranges of wavelengths throughout the universe. So what came next after I think you mentioned this already, the Spitzer work led to, what was the next big project
Well,
for
so
you, for you?
for me, after Spitzer, I went to graduate school, and at the
Mm,
end of graduate school, took up a position as a postdoctoral researcher at NASA at the Goddard Space
mm,
Flight Center in Greenbelt, Maryland, just outside of Washington, D.C.,
mm.
where I was developing similar detectors for an observatory that became known as the Herschel Space Observatory. It was led by
Okay.
East European Space Agency with significant NASA contributions. I was working on some of those contributions in those days.
Okay.
And I
Okay.
enjoyed doing that technology development. It was a really novel area where we were trying to
Mm,
push forward a technology that it only kind of sort of worked on the drawing board when we started it.
mm,
And within about a year, we had something as a very simple prototype that worked in the
mm.
lab and could meet the requirements for the spaceflight observatory. And it was
Okay.
an incredible time of cutting edge development. We had a great team that worked together
Mm.
spectacularly. And then we parlayed some of this into building instruments for an airborne observatory called SOFIA. That was a big
Oh,
telescope in a
okay.
747.
Yes. I was on a team that was trying to figure out ways to save that mission, JPL, about 13 years ago. And I was in a big room full of people and I asked, can we fly it upside down and look at the ground? And some of the scientists said maybe. The program people said, no, you cannot fly this observatory upside down. And I said, well, that's what I'm here for, is to ask challenging and confronting
Yes.
questions. Now, I want to go back to, you mentioned something that was a zero point 0.6 Kelvin. Is there a physical limit to which we could possibly cool things down to? And as I ask that out loud, I hear myself thinking, well, there is a theoretical physical limit and and an engineering limit. How would you address that question? I mean,
Right.
there must be a limit, because if you have a piece of matter somewhere, you've got a temperature above absolute zero. So there's got to be something there, right? But
Hmm.
how do you fill that in?
Well, so temperature is a shorthand way of referring to the total amount of energy stored within
Mm,
a solid object. in the motion that it has in various ways. So absolute zero is therefore defined by something which has no energy and has no motion of any kind anywhere in it. It's easier to think about energy in things like gases, like the air around us, because you can sort of sense that air is always moving. The particles of air are always bouncing around. And so you know that they have motion. But that's true of all objects. The thing about temperature is that it's better understood not as a linear scale from zero to something, but as a logarithmic scale, which is really how most of nature works. So rather than going up by units of 1 or 2, you go up by units of 10 times or 1/10. And so you can make a scale of any kind and say, well, room temperature is 300 Kelvin, for instance, or if you want, your room temperature might be 72 degrees Fahrenheit, whatever the number is, it doesn't matter. And then a natural thing would be, well, what's 10 times that temperature? Well, so if you're at 300 Kelvin, then 3000 Kelvin, that's the temperature of a very cold star, a red dwarf. You can just barely see it with your eyes. What's 10 times that? 30,000 Kelvin. That's about the bluest star you can make. A Sirius height. That's probably not even that hot, but roughly that. Okay, so is there something 10 times hotter than that, 300,000? Yes, you can start to get those temperatures and even millions of degrees as you move towards things like accretion disks around black holes, X-rays because they're that hot. Now, what about going the other direction? Start at 300 and go down a factor of 10 to 30 Kelvin. That's about the coldest parts of the interstellar clouds that are beginning to form stars. Before the stars have formed, so there's nothing heating them. They cool and they cool and they cool until they get to something like that kind of temperature.
You said 30 or 3 Kelvin?
I'm going to very roughly, because I'm only using factors of 10.
Sure.
And by the way, there's a great
But
book.
was that roughly 30 or roughly 3?
That was roughly 30.
Okay.
There's a great book called Powers of 10 that does this in linear scale.
I'm
doing this in temperature scale.
I had that when I was a kid. Yeah, I got one in here somewhere.
Good one. Yes. So if you want to go from 30 Kelvin down another factor of 10, 3 Kelvin, that's the temperature approximately of the cosmic microwave background radiation. That's the energy left over from the Big Bang. And so if you look out at the very edge of the observable universe, sorry, the screen doesn't let me gesticulate wide enough because it's so far away. That surface was very, very hot when the universe was very, very young at an age of something like 100,000 years. And it has been expanding and cooling ever since then. And it's now at about 3 Kelvin. And so when you look out there and you see as far as you can go with regular light, it's that, and it's about a 3 Kelvin temperature.
So it really doesn't have a physical meaning in the universe to go below 3 Kelvin anywhere.
So not a natural thing to go much below that.
Okay.
But, well, what's a tenth of that? 0.3 Kelvin. So you can get to 0.3 Kelvin using basically a fairly conventional kind of refrigeration. The refrigerator you have in your kitchen probably has some kind of working fluid, a refrigerant with an R number, I think. They typically work by a common way is a gas that expands and contracts. And when you squeeze it, it'll heat up. And when you let it expand, it will cool down. And so you have a compressor and then expansion coils that do the successive squeezing and relaxing that provides the cooling power that you have in your refrigerator that allows you to cool down your soda. So if you keep doing this at lower and lower temperatures with fluids that work at lower and lower temperatures, the lowest temperature fluid that is easily available as a single fluid is helium-3. I mentioned helium, which boils at 4 Kelvin. That's an isotope called helium-4, which is 2 protons and 2 neutrons, helium-4. Helium-3 is 2 protons and 1 neutron. It's a slightly lighter, and it has different enough physical properties that if you do as much of that sort of expansion of the gas above the liquid as you can get it down to about 0.3 Kelvin. And that's about as far as it goes, except that there's this really interesting property of helium that you can basically pour a little bit of helium-3 into helium-4, and you can make a dilute mixture of it. And the dilute mixture changes the way these 2 nuclei of these atoms interact in such a way that allows you to, by sort of relieving pressure, siphon off preferentially the warmer parts of that helium gas and leave the colder part. So you can easily go, this is called a dilution refrigerator. You can buy these commercially now, which is an amazing thing. And that can go down to 0.3 Kelvin or even approximately 0.003 Kelvin. That's roughly the coldest. So I've divided by 10 another 2 times.
Yeah.
Go out to companies and buy one of these and sort of off the shelf, take them a little while to deliver to you, and you can make 3 millikelvin in your home as long as you have enough space and power. But that's not all.
Yeah. Well, it seems I want to follow up on that, Stunell, but it seems like a milestone for civilization to make readily available a technology to create the coldest point in the universe
Yes,
on
we have.
demand. I just have to point that out for whoever's listening.
There are good reasons for doing this. And in fact, there's
Yeah.
a cold atoms laboratory on the International Space
Yes.
Station that was designed to get these ultra cold
Okay.
temperatures for measuring certain things, including quantum
Mm,
mechanical effects. I
mm,
won't even go into laser cooling, which is the next thing down, which is what
mm,
you have to do to get to these really low temperatures where you can have a small number of atoms that you keep sort of confined in a vacuum and you sort of nudge it with lasers to take
mm,
the heat out of it.
mm.
Nanokelvin temperatures are possible with this. But when you ask what's the scale like? How low
Sure.
can you go? Well,
Sure.
people are working on nanokelvin right now. You can keep pushing that technology and see if you can go another Greek prefix and get to
Sure.
picokelvin, or another one and get to attokelvin, or another and get to sorry, I missed femto and atto and
Mm,
zeptokelvin. There's no reason physically why those shouldn't be achievable. They're
mm.
not within the reach of any technology we have right now.
Fair enough. So, in contrast to that remarkable journey you just took us on, cosmic temperature scales, something else that's logarithmic is the elimination of bacteria in food. So, if you cook your chicken to 165 degrees, um, that's the recommended temperature, but it also makes it dry. If you cook your chicken to 164 degrees, you've let 10% of the bacteria survive roughly, and likewise upwards. And the reason that you can eat chicken cooked to 155 degrees, I think about this a lot when I cook, which is juicy and delicious, is because while you haven't killed all of the bacteria, you've killed enough of them that the average human immune system barely even notices. So there's a wonderful
Wow.
food YouTuber who has an MIT engineering background who is casually talking about this stuff while showing how to make turkey. So
That's
anyway,
really impressive, but I'm not a biologist, and the threat of salmonella is freaky enough to me that I would probably just go for the 165.
well, it's interesting. I don't blame you, but it's interesting to see YouTube chefs talk about this because they're all petrified that if someone cooks to 164 and gets sick, they'll get sued.
Yeah.
But I guarantee you that you've eaten chicken in the 180s routinely and never noticed. But even for me, that's kind of a tangent for this podcast. So let's move on.
Okay.
Much as I like to talk about cooking and really the application of physics and chemistry to cooking. Anyway, so okay, so you're at Goddard. How did you? I can guess because it's very close to DC, but how did you go from there to the DC to the headquarters position you're in now?
Well, I have always been motivated by a desire to understand and to
Mm,
build technologically advanced equipment that can help us understand things in the universe. And I mentioned working on things like Sophia.
mm,
Again, this is one of those sort of chance occurrences.
sure.
I got to know an astrophysicist who had moved from Arizona to Goddard fairly recently. His name's John
Mm,
Morse, and he had this idea for a way to measure galaxies in the universe in a
mm,
way to constrain dark energy. And this was back about 2006. Dark energy had been discovered in about 1998. They won a Nobel
mm,
Prize for it later. It's this amazing aspect of the universe. It appears like an energy that causes the universe's expansion to accelerate as though it's pushing everything
mm,
apart. And if you add up all the mass and all the energy in the universe, it's like 2/3 of it. And we don't really know much
mm,
about it at all still. And so he had this idea for a way to measure this and wanted to work with somebody who knew a little bit about how you built telescopes that could measure things. And so we started working on a project. The project was named Destiny, but eventually it was funded
mm.
as one of the concepts for a mission called the Joint Dark Energy Mission. And the joint part was
Okay.
it was going to be dual funded by NASA and the Department of Energy. We
Mm,
worked on that for a number of years. It went through some different versions in its concept studies and
mm,
ended up being recommended, as I mentioned earlier, by the 2010 Decadal Survey that said NASA should build this mission, except
mm.
they had renamed it to be W First, the Wide Field
Oh,
Infrared Survey. So
okay.
it was the outgrowth of JDAM
Sure.
because,
So,
uh,
so I heard
yeah,
all about that. In 2018, I was the proposal manager for IMAP at APL.
okay.
And so when developing the STM, the science traceability matrix for that, it was constantly referring back to W first. So I love to see all this stuff connecting in these things that I've seen, but didn't know the bigger picture. And so, okay, so go continue, please.
So that was the 2010 Decadal Survey that recommended
Mm,
this mission. At that time, I was working most of my time actually on Sophia still,
mm,
and among a few other projects. And in around 2013, around that time, the agency had been offered the opportunity to reuse some components that had been developed for
Oh,
space
okay.
telescopes by another government agency.
Yes. I remember that
And
now. Yeah.
they offered these to NASA. And so we began studying what it would
Okay.
be like to build then W first, now Roman,
Hmm.
using these assets that had been provided.
Mm.
It was a different design in several ways, but fundamentally it's kind of similar to what we'd been thinking. So it wasn't a great departure, but it was different. And so we studied that. And because it was going to become this new project, NASA headquarters wanted to establish what we call a program scientist, which is the person who
Sure.
sits at NASA's headquarters and establishes the policy and oversees
Mm.
the funding and operations of things. They needed somebody to do this for the new mission.
Mm.
My memory of this is that I was on a soccer field on a Saturday morning watching my kids running up and down playing soccer, and my
Mm.
phone rang. And
Mm.
it was Paul Hertz, the then division director for physics at NASA headquarters, and said, I need somebody to come down here and be the program scientist for NW first,
Mm.
just to get us started. Would you be willing to do that? I said, yes. I actually made him wait a long time before I gave him the answer. I said, yes. But I really love what I'm doing here at the Goddard Space Flight Center.
Uh-huh.
I totally invested in developing new
Hmm.
technologies, but I do know a fair amount about this mission. And so, yes, I can help get this started. I tell you what, I'll come there for 2 years.
Okay.
And I came to headquarters. And after 2 years, I hadn't really finished it. We weren't well enough started. 2015 was actually the year when we issued the what became the defining concept study report that said, okay, this is what we're going
Mm.
to build. But then we wanted to like set up and actually start building it.
Mm.
So I agreed to stay on for a couple of more years. And then it got to 2018 or so. And well, we were right in the heart of starting to get actual hardware. And I thought,
Mm.
wow, do I leave it at this point when we're just getting all the good stuff?
Sure. Well, I can see
So
using your framework from earlier about
Mm,
making decisions. The obvious one was
mhm.
you're not walking away now.
Yes. So I will say that in the early 2000s, I had set myself the long-term goal that I wanted to
Mm.
have a high-level role on a major NASA mission, and I never thought it was going to be this one.
Sure.
But I realized that I could stay and do that, and it wasn't what I thought I was going to be doing, but it did actually fit what I said I wanted to do.
Okay.
So there was a
Well,
disconnect between my mental picture and what I said I was going to
sure.
do, and I
Well,
rewrote my mental picture to what I said I wanted to do.
I completely relate to that because I always liked going out and giving talks at schools to kids. And after COVID, well, during COVID, that stopped. And it really has never picked up to the level it was before. And so now I have this podcast where I
Oh, yeah.
hopefully can reach even more people and tell fun stories like that. Sometimes a little more complexity like today, and sometimes a little more general audiences stuff. Although I would like to believe that general audiences would find this
Oh,
episode
I
especially
would I
interesting.
I hope there will be
Yeah.
people, general audiences, especially teachers who listened into this because they'll
Yes.
hear how you said that you like to talk to students. I love to do that as well. I booked
Yeah.
to talk at a middle school in a couple of weeks, and
Great.
I want to just put a little plug out here that
Mm.
there's a website. It's called NASA Engages. When
Hmm.
anybody, especially school teachers, but also people who are hosting public events, can
Mm.
request speakers from all across NASA, astrophysicists, engineers,
Mm.
accountants, everybody within NASA. If you want them to come and talk at an event, go to NASA Engages and put in a request.
Cool. And I especially like, no, it's great. I especially like that you mentioned accountants. Another goal of this podcast is that people with all kinds of backgrounds can see themselves at NASA and see themselves exploring the universe. NASA needs everybody from astrophysicists to graphic designers to computer programmers, IT people, everything. So actually, although I want to go back to the talks once, I've given hundreds of talks at schools, but I gave one talk at a nursing home. Have you ever done that?
I have
Really? Cool.
for a year or two, but yes.
Okay. I gave one and it was in about 2019. And there were two people there that were older than the rocket equation.
Oh my gosh.
And, and
That's old.
yeah. And there were many people there who were in their 40s during Sputnik.
Hmm.
And it was an extremely rewarding experience as I talked about these things that are not ancient history to me, but sufficiently far back in history that they're up there with ancient history. And to see people who were probably going to work, when they saw a newspaper about Sputnik.
Yeah. It's a
So
great thing. And actually, during the pandemic, sorry, not the pandemic, during the shutdown, if we hadn't had a shutdown, I was scheduled to speak at a retirement community in North Carolina. Again, it's the kind of thing that I love to do. And
yeah,
inevitably, the people who come to something like the kinds of talks that I give, somebody will come up afterwards and say, "Oh, I was the project engineer on Viking, that sent the
cool.
first landers to Mars," because the
Yeah,
retirement communities are full of these high
yeah,
achievers who did
yeah.
amazing things, and they just want to know how it's been going in the
Hmm.
decades since they retired.
Well, I at a wedding in 2012, I met someone who had been at JPL before NASA was formed, who had been there when it was an Army lab, and he was in his 90s then. But he said something that I won't forget quickly, which was that he was there before the eggheads took over. So I think he
Yeah,
left there in 1956. So that was a pleasure to speak with him. So okay, so
it would
you've been
be.
at headquarters since 2018 or 15, it sounds like.
2013, but
13.
that was temporary. Well,
Right. Yes.
I'm still here.
Yes. So you were, well, what did they used to call that? Not an
Detailee,
assignment? A detailee. Yes. I remember that.
detailee, or in
Yeah.
England you'd say it's secondment. So I I ended up staying here permanently. So now I'm actually
Sure.
a headquarters person,
Okay.
and the Nancy Grace Roman Space Telescope, which was formerly
Mm,
W1st, is less than a year away from launch. So it's been a
fantastic.
thrilling time. All of the hardware is there at the Goddard Space Flight Center. Just has to be finished the testing of it, basically, and ready to go.
Fantastic. So, looking ahead to the Habitable Worlds Observatory.
Yes.
So, when people ask me what my favorite color is, I say green, because if we see enough green in the atmosphere of another planet or in the sky of another planet, we may have some plants on our hands. And that is how nerdy I am. And I will say that to millions of people someday, possibly going through this podcast. So, that is the goal of HWO, correct? Something like that, seeing
It's
signs of
something
life in
like
an
that.
atmosphere.
Yes. Now, I'm an infrared astronomer. And so if you ask me what the
Okay,
best color is, I'd have to say infrared because,
fair
you know,
enough.
plants are actually infrared. If you look at them across a broader spectrum, they reflect more light in the infrared than they do in the green visible portion of the spectrum.
Interesting. I'm glad you told me that because it always annoys my kids when I say that. And now I can annoy them even more by saying my favorite color is
Ah,
in the infrared and sneak in
well,
some science
it's very nerdy,
education.
very egghead. Look at some of the older, I think they were Landsat images, those color
Mm,
images where they had detectors that went a little bit in the infrared. And so you
mm,
see the green areas, the areas a lot of vegetarian
mm.
are bright red.
Interesting. Yeah, one of my favorite tricks to do, this might actually work. One of my favorite tricks to do at schools, if you take a
Oh,
remote,
yeah.
okay, my webcam, oh no, almost got it. My webcam has a sufficient
Yeah,
filter in it
I think I see
that
the
it's not.
reflection. Yeah,
Yeah, that's just a reflection. But on a phone, maybe I can demonstrate it here. A phone sensor. Let's see. I have to line up the cameras.
right.
Basically, on some phone cameras, you can actually detect the. Not this one. It's too light in here. But if you turn off the lights in your room and you point an everyday TV remote at your phone camera, you might actually see on the phone screen the infrared light emitted from the remote that you can't see
Yeah.
with your eyes, but the TV can see. And I encourage everyone listening to go turn off the lights and try it.
Yes. It certainly should work, and probably older technology might actually work better because I suspect
Yes.
that I've done this before as well. I suspect that they've
Mm,
been getting better and better. All these things like your cell phone cameras have these Bayer filters that
mm.
give it the colors that you perceive, and I think they've been getting better
Yeah.
and better at making those so that maybe they block the infrared now.
Yeah. Yeah. I think I've done it with this remote and this phone, but
Mm.
not in the lit room.
Yeah.
So okay, so W first launching soon. So what's phase is well, without going into the whole story of how missions are selected and funded, at what stage, I'll say that instead of the formal phase, at what stage is the Habitable Worlds
Right.
Observatory project? What are the critical things that have to happen for it to launch, in my lifetime?
Well, hopefully that gives us a long window to
Yes.
launch. So the Habitable Worlds Observatory was recommended in the nominally 2020 decadal survey, although
Mm,
because of the pandemic, it was released quite a lot later than that. And
mm,
so we've only really begun to get started on it. It's at the stage where we are working on two thrusts. One is
mm,
the development of detailed enough mission concepts studies that we know all of the aspects of what it has to be able to do and what it has to have to do those things.
Mm-hmm.
So that's things like, what is the instrument complement? What does that look like? You want to
Mm-hmm.
measure the light reflected from a distant exo-Earth? Well, you're going to need coronagraphy, the ability to block the light of a star as a coronagraph. Block
Mm-hmm.
the light of the star so you can see the reflected light of the planet around that star. How well do you have to do that? What detector do you need to be able to measure the very faint amount of light that comes from that?
Mm-hmm.
We were talking earlier about detectors and counting photons and things. In the faintest possible scenarios where you're looking at a distant exo-Earth and just looking at the small amounts of atmospheric constituents,
Mm-hmm.
you might be down at counting one photon, one particle of light per minute of that order.
Wow, per minute.
Per minute. And when you think that when you look out at your room lights with your cell phone camera and
Mm-hmm.
you're looking at a few million photons per
Mm-hmm.
second, well, this is quite a lot. Quite a lot, frankly. And that's using a very large telescope to collect that much light. So it's not
Mm-hmm.
just the tiny little lens that you have in your camera.
Right.
There are many other examples of the technologies that we have to figure out how to develop for this. So that's coming up with a concept that tells you exactly
Mm-hmm.
what it is that you need to build. And at the same time, we are trying to advance the technological solutions that will enable
Mm-hmm.
those. So for instance, in order to be able to see these very faints, we would need to have exquisitely precise control of the wave front of the light. So light is a particle, but it's also a
Yeah.
wave. Wave front has to be exceptionally flat and precise. To make it flat,
Uh-huh.
you could say, well, we'll make all of our mirrors absolutely perfect, but the honest truth is that even if you did make them perfect, they don't stay perfect because
Uh,
they deform with changes in temperatures and the like.
yeah.
But make mirrors that deform. They're called
Mm-hmm.
deformable mirrors. And you can think of them being a
Mm-hmm.
little bit like a rubber mirror that you can bend a little bit, except that
Mm-hmm.
they bend by such tiny amounts that you're
Mm-hmm.
moving what looks to be at all times perfectly flat, but you're moving it by very
Mm-hmm.
subtle. If you want to go into the orders of magnitude, everybody is familiar with something like a meter. It's about a yard.
Mm-hmm.
A millimeter, which is a
Mm-hmm.
little thing like this, or a micrometer, which is 1 millionth of a meter, 1,000th of a millimeter, a nanometer, which is 1,000th of that, which is smaller than the wavelengths of light and of order the separation in of atoms. And then a
Mm-hmm.
picometer, it's 1,000 times better than that. We have to start sensing and controlling at the maybe not one, but tens or hundreds of picometer level. And when you think about sensing and
Wow.
controlling that, if you imagine a mirror that's made out of glass,
Yeah.
you be able to sense and move that mirror by amounts that are 1% of the size of a glass molecule. Tiny, tiny amounts. So
Well,
we develop these technologies
sure.
because we know that we need them and
Yeah.
know exactly how to build them. So there are people who are working on different approaches to making things like deformable mirrors, things like
Yeah.
photon counting detectors. And we're doing these in parallel so that in a few years, we should be able to make smart choices about which technologies need to be built for flight.
Okay.
So actually building the Habitable Worlds Observatory is something we're not doing for several more years because we want to have mature technologies to feed into that.
Right. Well, I can guess the answer to my next and final question, which is what's next for you? It sounds like this is what you're going to be doing for the foreseeable future.
Well, the great thing is that the Nancy Grace Roman Space Telescope is being prepared for launch
Mm-hmm.
sometime we're preparing for it in the fall of 2026. When we went through our confirmation review, which is the review where NASA
Mm-hmm.
actually commits basically to Congress and therefore to the American people that we're going to build this thing for a certain budget on a certain schedule, we committed to having it launched by May of 2027 for a certain budget.
Mm-hmm.
We're going to launch early and we're going to launch under budget.
Great.
That's my prediction.
Fantastic.
It's very well managed, not by me, but by
Yeah.
other people who have been doing all the hard work, the hard engineering work
Mm-hmm.
at getting this thing done. So we're going to have the Roman Space Telescope launching in about a year.
Mm-hmm.
It's going to be a phenomenal mission because of the amount of astronomical data it takes. As I said at the very beginning, it's a survey telescope. It's a survey machine. It has the same size as the Hubble Space Telescope and therefore the same sensitivity and the same sharpness of image, approximately speaking. But it has a camera that is vastly larger. Instead of being a 1 megapixel camera like the infrared camera in
Uh-huh.
Hubble, we have a 300 megapixel infrared
Wow.
view. And we are substantially more efficient because we can move the telescope and stop and take photos several times faster. So we can map the universe about 1,000 times faster than Hubble. So all of the pictures that
Wow.
Hubble has taken over the 35 plus years of its lifetime, Roman can do that in a couple of months, and it's going to last for
Fantastic.
years. And all of the data go publicly available as soon as we get them into the archive, which means
Mhm.
minutes, hours, days, weeks before
Sure.
all the data are available to everybody. We start downlinking data as soon as it's in operation, so early 2027, and
Mhm.
we feed data down at a rate of about 11 terabits a day. Ends up being
Mhm.
about 20 petabytes in the archive after the first 5 years.
Okay.
It'll usher in a new era in astronomy because we're going to be saturated with phenomenal amounts of data. And I'm just looking forward to watching scientists around the world
Mhm.
capitalizing all of this and making discoveries that I couldn't even have imagined when we began on this path almost
Sure.
20 years ago.
Now, once that is in operation, are you gonna move on to habitable worlds mostly, or is that so far ahead where you don't know yet?
Well, my role as chief technologist for astrophysics is to help shepherd along the technological
Okay.
development that will put us in a position to begin building it. I don't
Got it.
anticipate that I'm going to play that role. I've already had one spectacular mission that I got to oversee. I don't
Mhm.
want to hog all of the great missions, but I want
Mhm.
to make it possible for whoever my successor is, if you will, on that
Sure.
project to be able to take the Habitable Worlds Observatory forward through its design and development and construction and launch.
Mhm.
And I want to watch that, and I'll be really eager to see what it discovers because that ultimate goal, it's one of many, but the ultimate goal that I
Mhm.
think resonates with so many people is try to answer that question. Is there
Yeah.
life or elsewhere in the universe? I don't know, but I would guess that life could be common enough that if we survey a few dozen planets, that we may see signs of life. We won't know if it's things like humans or things like slime mold,
Sure.
perhaps because we're just
Yeah.
seeing what's in the atmosphere. But I think that
Yeah.
it's
Hey.
reasonably likely, and that we will know this in our lifetimes.
Yeah.
We're privileged to be alive at a moment when not only can we ask this question, we know how to answer it.
I think about that a lot. I agree. I think that we may well find something. And that's what I tell kids or everyone who will listen and some people who won't. That's what I tell them. I think we may well know that certainly this century. I
I
think
think
that's
you're right.
about the best possible place to stop for today. I
Well,
really
maybe I can add
appreciate.
one more
Oh,
thought
please.
for all the
Sure.
kids that might be watching this. I said that I'm not going to be the person who leads the Habitable World Observatory. Somebody else
Mm,
will build this, and then it'll produce all of its
mm,
data. And the people who actually research it,
mm.
that's going to be the people who are in elementary, middle, high school right now.
Yeah.
So one of the things
Yeah.
that I often start and then end my presentations to schools is this:
Mm.
your generation will discover aliens. I
I
believe it
like
to be
that.
true.
Yeah. Yeah. Well, that's an even better place to stop. So once again, thank you so much for joining me.
Thank you, Jeff.
And thanks
It's
to
been a pleasure.
everyone. Likewise. And thanks everyone for listening. That's it for this episode of the Space Madness podcast. We'll talk to you soon.